Okay, so let's try this. So in 19.4, number 24, they tell me that there's a vector field R that's given by x, y, and z. And then further, there's a different vector field F, which is given by R divided by the magnitude of R cubed. Cool? And then they tell me that I'm supposed to initially here calculate the flux of F out of the unit sphere. Flux of F out of unit sphere. Okay. How do I start calculating a flux?
Divergence.
That seems like a good idea, right?
So that's first.
So wait, hang on. Careful. So you all have a new toy that you like using, right? The divergence theorem?
Don't break the toy.
No, just make sure you're allowed to use the toy on this problem, right? Like,
Simple, smooth.
keep in mind, you have the divergence theorem, which is the kind of math analogy of a 10-pound sledgehammer. Is this a problem in which a 10-pound sledgehammer is applicable? In other words, you want to check and make sure that the tool you need isn't a soldering iron first. Right? So a little careful with your big hammers. The big hammers in here are the divergence theorem, Greens, and Stokes. Right? All of those are kind of the equivalent of a big tool. So just make sure you're using the right big tool, or that you're allowed to even use a big tool.
They won't just
You guys good with
crush
this?
the entire thing. Yeah.
There would be, I see, it's a
So,
little bit of a weird thing if the magnitude is 0.
Yeah.
okay,
So that
good.
would create a mixed position.
You guys see that? There's some kind of a problem
At the origin.
at the origin with my vector field F. You guys see that?
Oh.
So what did I need to apply the divergence theorem at all?
In order to have all the points within the boundary.
Yeah, so I needed outward orient. So I needed a surface, right? A two-dimensional orientable surface, oriented outwards. So I need a surface, check, outward, check. What else did I need in there?
Is it simple
Differential
closed or
surface.
something like that?
Yeah, I needed it to be smooth. I didn't need simple here.
A closed?
The analogy of simple here is outward oriented.
Don't we need closed?
Yeah, I need some kind of closed, right? That's enclosing a region. Is my unit sphere, does that enclose a region?
Yeah.
Yeah. It needs to enclose a bounded region, right? Okay, it does. Cool. What else did I need? Yeah, I needed continuous partial derivatives. You guys see that? So your F, right, is the vector x comma y comma z, right? Divided by, ooh, that's weird, right?
It's a scalar applied to a vector.
Yeah, so that's a scalar function applied to a vector, right? So the output of that thing is going to be a, it's going to be a scalar, right? This guy's going to be a scalar on the bottom.
Yeah, the guy
And then
on the
the result of the division is really a result of scalar multiplication. So I'm going to get a vector field out of this, right? So they were right about the categories of F. It's this scalar function that's causing me confusion. How long is the vector R?
Well, it depends where you're at, right?
Yeah, it depends on where you're at.
It's this.
So what's the magnitude of R? I think I can figure it out.
And that would be the square root of x plus y plus z, or?
Yeah, that'd be the square root of x squared plus y squared plus z squared, right?
Okay.
And then all that keeps
Yeah, so then I need to cube all that. So I got x squared plus y squared plus c squared all to the 3/2 power. You guys with me on this? Okay.
Can't ever be negative. That's nice.
Yeah, that's good, right? But I need to take derivatives, right? Trying to calculate the divergence of this thing, right? I'm going to have to calculate some derivatives. Shit. Right? So there's this, like, in this statement, there's a thing about continuous partials on your region and a bit more. And as far as I can tell, I don't even have a function that's continuous on that region, right? So the divergence theorem is kind of, yeah, not really the tool you want, right? Like you could try to hit this with a sledgehammer, but there's the possibility that that won't be good. So how do I calculate the flux out of the unit circle or the unit sphere if I can't use the divergence theorem?
Use the median.
Yeah, just crank on it, right? Okay, so you're going to need to parameterize the unit sphere.
Yeah.
Correct. Right? So it's okay. We can do it.
Yep.
So we just need S of, oh, whoops, sorry, wrong thing, jumping ahead.
Oh yeah, we've done this before.
We need S of theta and phi, right?
Yeah.
Which we've done before, thankfully.
It's
Okay,
unit
so we
sphere,
got,
it's sine phi cosine theta.
where'd your row go?
It's one.
It's one.
Yeah. Oh, thank you.
You guys all see that, right? I'm parameterizing the unit circle, or the unit sphere, rather. So the row is 1. So I got sine phi cos theta, sine phi sine theta, and cosine phi. Are you good with this? Okay. Where's that go?
Yeah, that goes into R.
Which thing are you integrating here?
Yeah, from there.
Flux of F, right? So this problem is a little funky, right? Because they made a kind of a vector field, and then they made a different vector field out of that vector field. You guys see that? And I'm trying to calculate the flux of F.
So it goes.
So it goes in R, which goes into F.
So it goes into R, which goes into F. Yeah. You guys all see that?
Yeah.
Yeah.
Luckily, the magnitude of R on this surface is 1.
And we can prove that.
You guys see that? So all I get here is this thing. So I got sine phi cosine theta, comma, sine phi sine theta, comma, cosine phi. And now I need to dot with, good call, D area. Because, so this is going to be over this sphere, right? You guys all with me on that? Oh, I didn't teach you guys this trick. Shit. Never mind. Yeah, good call. Right. Figure out what the area is. Yeah, we should just take what we took from the last one, or we could save time and like flip into the back of the book, or flip into the book and be like, hey, where's that thing for, what am I looking for in the book? I'm looking for the one for spheres, right? Okay, so yeah, it's f of r and theta dotted with the sum of the components times, yeah. Okay, so you put in the thing. Oops, that's the wrong spot. So you sum the components, so you got sine phi cos theta plus sine phi sine theta plus cosine phi, and then you need a r squared, which is, what's your radius of your sphere here? 1. So you get a sine phi d theta d phi. And then where are your phis range?
Wait,
Shouldn't
yeah,
that be-
commas
shouldn't-
instead
Yeah,
of
commas
pluses.
instead of pluses. They had IJK in there.
Probably, yeah, thank you. Good, cool. That
So
makes sense.
even with this, we still need the rho square sine phi. Even though we're doing like a weird double integral with spherical.
Yeah, that'll come out in your cross product.
Oh,
So if you calculate that cross product, you'll get this stuff. So you'll get from 0 to pi, ooh, whoops, pi goes on this one.
No.
No, the pi goes on the other one.
Yeah,
What goes on this one?
2 pi. 2
2
pi.
pi.
Yeah.
Cool. Good. Next. Now what?
We can do the dot product, and by the way, we kind of, if you go through the proofs, you find that the dot product of those two things is 1.
Yeah, don't go through the proof. Just look.
It's the same thing.
That's going to be x squared.
It's the magnitude squared.
Oh,
That's going to be y squared, and that's going to be z squared, right?
which equals rho squared, and rho is 1.
Which is going to be the magnitude squared, which is in this case 1, right? You guys see that? So that whole jazz is 1.
We get sine phi.
So we get two pi times the integral from 0 to pi of sine of phi d phi, which is 4 pi,
Which is the surface area.
which is the surface area
There's-
of a sphere. Why?
Those vectors are all unit length.
Okay. So this vector, your vector field here, right? On the unit sphere. So on the place we're talking about, right? These are outpointing length 1. Okay, see that? They point straight out and they're 1 unit long. Straight out is perpendicular to the surface of the sphere, right? And they're all 1 long everywhere. So this is just a fancy ass way to add up the surface area of the sphere.
That would only be the case with a radius of 1, right? Though,
Yeah.
If we went out a little.
Yeah, if we went out a little further, we'd have to scale by the radius somehow.
Or you could just remember Gauss's law.
Yeah, or you could play with Gauss's. This is the vector field that's in Gauss's law. So I got 4 pi out of this. Yes. And I did it without the divergence theorem. And why did I do this without the divergence theorem? Because the divergence theorem wasn't going to work. So, what?
I was wondering, you say that like there's no flux through like an edge or a point because it doesn't have volume. So if you have a 0, 0 point at the very center of that, why does that matter if it's not going to have any flux anyway? You can't flow through a point.
It's not, so that's not me worrying about applying the divergence theorem. Isn't me worried about flux through a point. It's me worried about divergence at a point. And what I'm doing when I'm adding up divergence, right, is I'm taking a triple integral and I'm adding up all of those little divergences at every point. And I would say normally like, hey, that point in the middle has 0 volume, so who cares, right? But what's the divergence there? I don't know. Let's calculate it. So that's what part B is anyway. So let's calculate the divergence there, and I think it'll answer our question. So remember, we got 4 pi. So, okay, I got to this. I got that my vector field F is given by x over x squared plus y squared plus z squared to the 3/2 power, comma, y over similar. Oh, not similar, the same. And z over, yeah, the same. Okay, now I would like to calculate the divergence of this thing. Right? Yeah, nasty thing, right? So I need the partial with respect to x of x. Uh-oh. You guys remember how to use the quotient rule?
Let's see. F.
Let's just use the product rule.
Good, let's just use the product rule. So I'm rewriting the bottom, right? X squared plus y squared plus z squared should be to the 3/2 on the bottom. So I'm rewriting it as
Negative 3/2. My gosh, what was I even thinking? My gosh. I'm sorry.
We've
Cool.
all done it.
It's okay.
We've all done it.
okay. And then, oh, whoops, sorry. Partial with respect to x of that stuff. And then what do I want to do?
Plus partial with respect to y.
Plus the partial with respect to y
Of the same thing with y.
of the same thing but with y's instead.
Are we trying to see how the diff breaks right now?
Yeah, and really part B actually says just calculate the divergence. So that's what I'm doing. So
Oh no.
similar sub y and similar sub z. How about that? You guys good with this? I think I really should be able to just calculate one of these and then I can plug them all in.
Yeah.
Okay, so when I take the partial with respect to x of this junk, what do I get?
Let's see. So x squared plus y squared plus.
So it really would have been a lot better if you'd remembered
Yeah.
the quotient rule, but whatever.
Do you remember it? You could do it. Save us some time.
Look, it's not my job to save you time. It's my job to illustrate to you good mathematical techniques. No, it's too late. They already forgot it. No, it's too late. They already forgot it.
I know what it is, but it's like honestly.
Okay, so I'm just taking this one. I know it's going to suck, but that's the way it is when you forget the freaking quotient rule. Okay, so you smile to yourself.
No.
Shut up. The rest of you all who have forgotten the quotient rule, frown to yourselves and learn. So, how's the product rule work again?
You left
F part,
you left.
F derivative of x, gx plus.
Okay, so one of these will be easy, right? Take
Yeah.
the x derivative of x, you get 1, and then multiply by this other crap. So you got x squared plus y squared plus z squared, all to the 3/2.
Negative.
Thank you. And then
Adding it to the other way around.
add, okay, so now I need an x,
And then,
and then I need the partial with respect to x of that junk.
so 2x
Which is
times negative 3/2.
So I got a negative
Basically,
3/2,
then a 2x.
and then all this crap.
Yeah.
Oh yeah, let's put the 2x in there. And then x squared plus y squared plus z squared
To the negative 5 root 2.
to the negative 5/2.
See, so it's actually easier to do with the product rule than with the quotient. Because
It's
with
just-
the quotient rule, you'd be squaring that stuff and then, adding and
If you square it,
it'd be messy.
Sure. Okay. I'm gonna have to add all this crap together here in a minute anyway, so I guess we may as well leave it like this. Cool. Let's simplify a little
simplify
bit,
that to a
right?
negative 3x squared.
You could just factor out one of those nasty.
Don't factor things out. You're gonna add them together in a second.
Oh, yeah.
Okay, so I have here a 1 over x squared plus y squared plus z squared to the 3/2 plus What are you left with out of that, John?
Negative 3x squared.
So minus 3x squared, and then over
X squared plus y squared plus z squared.
x squared plus y squared plus z squared,
Parentheses 5 times.
all to the 5x. Okay, so you trot that over here, and you cram that in for the partials, right?
And they would all be the same, right? It would be like negative 3y squared, negative 3z squared for those.
Perfect. You guys all see that? So 3 of these terms are all going to be the same, right? They're going to be 3 over x squared plus y squared plus z squared to the 3 halves. So that's the 3 first terms, right?
Yeah.
X. This guy for the x, this guy for the y, and this guy for the z. And then there's a minus 3. And then there's, well, there's one with an x squared, one with a y squared, and one with a z squared,
Oh,
right?
you're factoring out the x. Okay.
So there's an x squared, a y squared, and a z squared, right? And that's all over x squared plus y squared plus z squared
In parentheses 5 halves.
to the good 3 halves plus 5.
Where'd you get
Oh,
the
ha,
lone
ha.
3 on the left of the, is that that one?
Those 3?
Yeah.
So when I'm writing this down, I'm writing this guy once for x, then I'm writing this guy but with a y. So let me call this thing, I'm going to call this thing Steve, and I'm going to call this thing Bill sub x,
Bill.
right?
Skrillex.
So this guy is really going to be a Steve
Skrillex brother. It's
plus
Billy.
a Bill sub x, right? Plus a Steve plus a Bill sub y plus Steve
Billy.
Yeah, Billy.
plus Bills, right? So I've got my 3 Steves.
Billy.
That's this dude. And then I got my Bill X, my Billy, and my Bills. And out of those, I have factored the thing that's in common, which is a minus 3 over x squared plus y squared plus z squared to the 3 halves plus 1 power.
You can count it.
And the reason I wrote it as 3 halves plus 1 power is,
Because you gotta remove 1. from
yeah,
the
you can
top.
drop 1. You guys see that?
So you become negative 3 over that to the 3 halves.
So I got, yeah, so this stuff, and one of those, onesie out.
That should allow you to, yeah.
So you got 3 over x squared plus y squared plus z squared. Oh, what the hell? You have 3 Steves, and then somebody took 3 of them out back and murdered them. How many Steves you got left?
Yeah. You just got Billy.
So at every Bill, there's a
So
Steve.
what you have is this. Well, almost.
Assuming that X, Y, and Z are not 0.
Yeah, you guys see that? Like, 3 Steves minus 3 Steves is always 0, except for where Steve already exploded and broke everything, right? So there's a little asterisk here, right, on this equal sign where I simplified, that says, hey, I just modified the domain of my function. I just plugged a hole, right? You guys all see that? So there's a problem, well, so except when x squared plus y squared plus z squared is 0, right? So like, yeah, the divergence is 0 except at the origin where apparently it's probably infinity or something.
So would it be undefined with the infinity?
It's a very,
Yeah, it's undefined.
very large
So
source.
that's the same.
And it, yeah, there's multiple ways, there's more ways to be undefined than there are to be infinity, right? You guys see that?
Yep.
But I sort of suspect that this one is that it's infinity at the origin. The reason I expect that it's infinity at the origin is that I was getting flux through a sphere, right? But the only way to get flux through a sphere with no creation of anything anywhere,
No divergence.
right?
Yeah.
Except for at 0, would be if something's being created at 0.
So we just,
So that's why I can't add it up, right? Because if I try to add it up, it's like, yeah, it's 0, it's 0, it's 0, it's 0, except at 0, like at the origin where it's kablooey.
so it's the Big Bang sort of.
You guys kind of see that? Yeah, I mean, this is sort of the math that goes into the idea of the Big Bang. Yeah.
Huh.
You guys cool? So what happened is, oh, and actually part C is now really easy because part C is about something about a cube with bigger sides than your sphere. So what I found out right at the very beginning was that the flux through the unit sphere was 4 pi. You guys all remember that?
Okay.
And then they're now asking me about some kind of a cube.
Even smaller lines.
Yeah, it's more dotted because you have to look through the sphere to see that.
Double X-ray vision.
Double.
I don't know. It doesn't matter. All that matters is that it contains it. What does it actually say?
It says to calculate the flux out of a box with side 10.
Yeah. So it says the sides are 10 long.
Oh, yeah, that would be way
So the point is, it doesn't actually matter. It just has to be bigger. And so if I look at the divergence theorem, anywhere that doesn't include 0, I'm okay, right? So they want you to do the flip trick here. You guys see that? So what I found is that the divergence is 0 everywhere except 0. And then if you add up the flux through the unit sphere, you get 4 pi. You guys see that?
Okay.
So if I call this thing, I'm going to call this box minus sphere, very creatively. Right? And I want to take the flux for part C of F through box. Now they actually want me to calculate the flux through the box, right? I could set up an integral to do that. Or I can say, hey, the flux of F through the box I can't apply the divergence theorem directly to this, right? Why can't I apply the divergence theorem directly to the box?
The sphere is contained within inside of it, and that has a non-continuous partial.
Yeah, really this thing, right? Like, the partials still aren't continuous everywhere in the box. Because they weren't continuous in the sphere, and the sphere is inside the box. You still have the same goddamn problem, right? So you still can't apply the divergence theorem directly to this thing. But you can apply the divergence theorem to the area in between the two. You guys see that?
Gosh.
So like this is what I want. So what I'm going to do instead is apply the divergence theorem. So I'm going to think about flux of F through box minus sphere. Right? And this I can apply the divergence theorem to. You guys see that?
Yeah.
So I'm going to get the triple integral of 0, right, dv. But what's this over now?
0 to 10, 0 to 10, 0 to 10, right?
Well, no, it's from the sphere to the box.
Yeah, it's between the sphere to the box, right? You guys see that? And that's probably going to suck to write down. Thankfully, I don't need to write it down because I'm integrating 0. So this is going to be 0, right? But now I haven't calculated the thing I wanted, right? The flux through the box. I got the flux through the box minus the sphere. I found out that's 0.
Then you
So the
just
flux
add the
of the
sphere.
box is negative out of the sphere.
Yeah, so what I found out, right, is like I want this guy. So I'm going to write this guy as the double integral, right, over box minus sphere. Right, of FD area. But those are actually two separate surfaces, right? So to do this, I'd parameterize one and then parameterize the other and add the results, right? You guys see that? So I'd say, okay, so this is the double integral over the box of FD area minus the double integral over the sphere of FD area. Oh, except I just lied, because I want plus. I just said it was plus. You guys see that? So what's where'd the negative sign, how does the negative sign come into this business?
The algebraic software.
Yeah, so what's the orientation? So I just did flux of box minus sphere with the divergence theorem, right? You guys see that? Like this thing right here, that equal sign, gave me an orientation for the sphere. What was it? What's the divergence theorem say about the thing you're integrating? It needs to be oriented outwards. What does oriented outwards mean in the context of being in between the box and the sphere?
Oh.
Well, no, it's
Oh,
I didn't even know where
it's
counterclockwise
into
lived
the
here.
region.
Yeah, so outward is away from the region, right? So if you're standing in between the box and the sphere, oriented outward is on the box, right? It's out.
But it's also into the sphere.
But in the sphere, it's pointed into the sphere, right? You guys see that? So that is the opposite of what I calculated earlier. Yeah, so that'll be negative 4 pi. So what I get is that this is the flux through the box minus 4 pi. You guys see that? And so if you chase the beginning and the end of this thing, you'll find that you should know the flux of the box, which should be 4 pi. So that's me saying this. That's saying flux through the box minus 4 pi has to be 0 from the divergence theorem and a calculation I did earlier.
And Gauss's law.
And Gauss's law, which says that over any closed region, the flux of a point electrical source is always 4 pi.
The potential from a source.
Oh yeah, sorry, the potential from a point source. Cool? Questions, Steels? So I need, yeah.